All right, here we go. Unit 7, Lesson 8. We're going to be doing a second type of volume finding with calculus here. We're going to call these solids with known cross sections. And so these are not rotations. That's the first thing I want to point out here. These are not rotations. They're going to be a different type of cross-sectional area. But I will start out with a reminder of the one cross section we've done so far, and that's cross sections by rotations. And so if we had this function here, something like the square root of x, and I said, what is the volume when you rotate that around the x-axis, right? So you got sort of like this imaginary z-axis that's sticking out here, and you rotate it 360 degrees around, you'd wind up with this cup shape, right? And so we found these volumes, and the way we found the volumes was we imagined that you slice straight through this thing and then you look into it, and what would you be seeing? If you look into a cup and you've cut into it, you would always be seeing a circle. You know, larger circles towards the end, smaller circles towards the beginning, but circles nonetheless. And so what we did was we found that you could integrate the volume of sort of infinitely tall, small, like technically cylinders, right? You could just go left to right, and your dx serves as the width of these cylinders, and so you'd have, you know, the definite integral from a to b of pi times the radius squared, and it's the dx that gives these depth as you move left to right. And so the idea here is that there are other ways we could form solids without actually using rotation if we just sort of come straight out of the paper. And so here's the first and simplest example here. What if we just had squares? What if we just had squares? Well, if we look at those squares, and you can imagine, right? Imagine that there's not like 8 post-it notes, but there's like 1,000,000 and they're smooth. You can imagine that being a 3D shape. Well, the idea here is still the same. We still want to integrate left to right with respect to x, but instead of having pi r squared, what's the area of this square surface going to be? Well, the area of a square is just the side length squared. And it turns out that we can find the side length squared. It's just the distance between these functions, in this case, f minus g. And so if we have the side length, the area of the square would just be f of x minus g of x, right? This right here is the length of that base, which in a square is also the height. If we square it, we'd get the area. And if we want to turn that area into a volume, just like we did with the circle, we would integrate from left to right. Let's call it from point A to point B. We'd go from A to B. We would find the area of each of those squares. They sort of get larger and then smaller by squaring it. And then it's the integral with the dx that gives these things volume. It gives them, we basically cut it into an infinite number of thin slices, and we integrate those all together. That's what gives us volume. And so that's the first cross-sectional area that you might be asked to find. The next one, sort of one step up here in difficulty, but really this is a natural one here. If I tell you, and so each time you're going to be told what the shape is, and you have to pay attention to that. Next step up in difficulty might be an isosceles right triangle. So 2 key words there. Right triangle, meaning 90 degrees for one of the angles. Isosceles, meaning 2 of the 3 sides are the same. And so if this is side A, so is this one. The hypotenuse is different. But the reason this is the next one that we do is because it's literally just a square cut in half. And so if you can find the square, you can find the isosceles right triangle. It's just 1/2. We usually say the area of a triangle is 1/2 base times height, but if base and height are the same, we can just square it. So it's the same thing as the square, it's just half of the square. And so it's the same thing. We would take the volume, let's put the 1/2 out front, looks a little cleaner that way, from A to B of f of x minus g of x squared. So same idea, it's just half as much. And so again, the idea here is f minus g tells us the base, which also tells us the height of one of these triangles. We can find their area, we can integrate to turn that area into a volume. Now here's the killer here, equilateral triangles. And so Equilateral triangle, remember, all three sides are the same. What makes this tricky is we still find the area of this triangle by doing 1/2 the base times the height, but we do not know the height. And so I'm going to prove this, and then it's something you can kind of have with you, and you do kind of want to try to have this tucked away, memorized in your brain. But if you get stuck on an AP test and you have a minute, here is how you would find the area of an equilateral triangle. I'm going to go ahead and I'm going to replace here. I'm just going to say S is equal to f of x minus g of x. Let's just call that S for side length. So that's this side length, it's this one, and it's also this one. Well, if we drop a height down, we now have two isosceles triangles. And we can use the Pythagorean theorem. If I call this right here one of the sides of this three-part triangle, well, it would be half of S, so it would be S over 2. And the Pythagorean theorem tells us that a squared plus b squared, and again, only for a right triangle, and what's b in this case? B is the height. B is this height that we want right here, and all of that is going to be equal to S squared. And so we can solve this out, right? I'm not going to dwell too much on it here, but what we would have is S squared over 4, so 1/4 of S squared, plus H squared is equal to S squared. And as long as we can get H in terms of S, we're good to go, because we can get S in terms of F and G. And so what this ends up giving us is H squared is equal to 3/4 S squared. And we take the square root of both sides to get to just what H is. And that leaves us with H is equal to S root 3, right? The S squared can come out, and so can the over 4 as a 1/2. So we get the height is S root 3 over 2. All right. Now, the thing you can memorize if you so choose is that, remember, we're calling this is S, 1/2 the base times the height. So this would be 1/2 times S times, we just found what the height is, S root 3 over 2. And so this gives us 1/4, right? 1/4 of S squared root 3. And so if we kind of rearrange this and put S back to being f of x minus g of x, we would have the square root of 3 over 4 times f of x minus g of x squared. And so the one thing you would memorize here is, okay, if I can find this length here, which is usually going to be like f minus g or something like that, or just like f if it goes down to the x-axis, it's this root 3 over 4. So it's root 3 over 4 times the side length squared. That's the area of an equilateral triangle. If we add this all up, same idea, we can bring this root 3 over 4 out front, the definite integral from a to b of f of x minus g of x squared. That's the hardest one. It's the one I think comes up the least often, but it could potentially come up. You want to be really good at the square. You want to be really good at the isosceles triangle. And then this next one, the last one we're going to go over here, is this semicircle. The semicircle is really straightforward because, again, it's just half of something that we have done before. And so let's look through this. But you do have to kind of think about it carefully because it does end up getting a little bit tricky here. So let's say we wanted to find the area of this semicircle, because all we have is this long side length here, right? And I think my guess is people's gut feelings is they're going to say, oh yeah, it's a semicircle. So it's going to be 1/2 times pi times f of x minus g of x squared, okay? And this is not true because f of x minus g of x, if you are not rotating, no longer represents the radius. the radius is half of f of x minus g of x. And then the semicircle is half of that, right? So the area of the semicircle is 1/2 pi r squared. But what is this radius? Well, it's 1/2 pi times f of x minus g of x all over 2 squared. And so if we do that out, right, the 2 would get squared. This would be the same thing as saying the area is equal to 1/8, right? Because this 2 squared becomes a over 4, and you can pull that out. 1/8 pi times f of x minus g of x. I guess that no longer needs to be in a fraction. F of x minus g of x squared. So you could also, I think you could also write this, if you like to write it this way, you could say this is 1/2 times f of x minus g of x squared. And maybe that would help you see that 1/4 turns into a 1/8 better. The volume there, same thing. I don't know why I just drew a square root symbol. The volume is equal to, we'll bring that 1/8 pi out front. Again, these are not things you want to memorize. You want to just be able to kind of think these through, with the possible exception of the equilateral triangle of f of x minus g of x squared. Okay, so let's just see a couple of examples here using real functions here and wrap this one up. So let's see here. Let's see what I got here. Let's actually, I'll fill these out, but I actually want to skip just sort of like straight to the one example from a delta math that I did here. So I'll post those in the notes, but I think 15 minutes is about the maximum usefulness here. So let's go ahead and do this one. Let the region R be the area enclosed by the function f of x is 2x squared and g of x equals 3x. Okay, well, then this one's 3x, and then this one's 2x squared because it's curved. That one's easy. If the region R, so that's this region here, is enclosed, and that each cross-section perpendicular to the x-axis. Okay, so the cross-sections, they run north-south because it's perpendicular to the x-axis, is an isosceles right triangle. And so this right here, if I'm going to blow this up, is the base. It's kind of hard to draw, but if I think about these here, it's going to be the base of an isosceles right triangle. Find the volume of this solid. Okay, well, what you want to imagine here is a bunch of these sort of isosceles right triangles coming out of the page into the z-axis. They're going straight up, and we need to find the area of each of these triangles. Well, it's just going to be 1/2 times the base squared, 1/2 base times height. And what this base is equal to g of x minus f of x, right? Because in this region, g of x is on top. And so this is going to be 3x minus 2x squared. And so that's going to give us this right here. And so if this was a calculator active question, I could go ahead and I could take this over to Desmos. We would have to find these two intersection points here. So let's go ahead and actually, I'll show you how this works. Let's pull up Desmos here. Let's actually graph this. Oh, come on. Let's pull up Desmos. Pull up Desmos, he said, and it worked. There we go. Man. What the heck? Can I not do the same screen anymore? There we go. All right. So we've got Desmos. Let's check it out. If we have 3x and we have 2x squared, all right, we're going to zoom in on this one. Okay, we need to go up until, 1.5. So from 0 to 1.5, we're going to be taking 1/2, and we can write this 1/2 on the inside. I kind of like to sometimes. 1/2 times the base, which will be g of x, which is 3x, minus f of x, which is 2x squared. And so let's just go ahead. Let's take that integral here, I n t, from 0 to 1.5 of Let's put this all in. Well, let's do the 1/2 first because the 1/2 doesn't get squared. Careful, right? It's 1/2 base times height, which is 3x minus 2x squared. Careful, all of this is squared as well. And so that means I probably, can I get away with just putting a dx here? I don't know if it'll let me do that. Yes, it will. Okay, so what we have here is that this area is equal to 0.506. Or sorry, this volume here is equal to 0.506.